Hi everybody. So today's video is going to be about task 1.6, which is the sixth task from Module 1 for Math 1. We have two learning targets for today. The first is I can create an explicit and recursive equation for a situation that can be modeled as an arithmetic sequence. And the second learning target is I can create an explicit and recursive equation for a situation that can be modeled for a geometric sequence. Now, today we're going to focus on what are called explicit equations. So our goal is going to be to create, which means to make, an explicit equation for both arithmetic sequences and create an explicit equation for geometric sequences. So we're going to look at both types of sequences that we've been learning about, and we're going to be working on creating explicit equations for these scenarios. Now, in order to sort of think through how we write an explicit equation and where this thinking process comes from, we're going to start by looking at the following table. It says Diana starts the year with 10 demon dollars and she earns 2 demon dollars each week. Now, if we were to make a table for this type of situation, because Diana starts the year with 10 demon dollars, we can see that for week 0, we have a value of 10 for number of demon dollars. And since she earns 2 demon dollars each week, we can see that the value for the number of demon dollars, it increases by 2 each time. Now, up until now, when we have looked at patterns in a table like this, we have typically been looking at what I call down the table. And what I mean by that is, if we go from 10 to 12, which is going down the output values of the table, we are adding 2. And we can see that that makes sense because she earns 2 demon dollars each week. So that pattern kind of shows up in multiple places. It shows up in the words that we can read, and it shows up in the table if we go down the table. And that pattern is consistent for the entire table. Now, our goal for today is going to be writing an equation that will allow us to figure out the number of demon dollars for whatever week we want. You'll notice that this last box has an X. If we were to let X represent the week number, could we figure out by calculating using an equation the number of demon dollars that she would have? In order to do that, we need to do a little bit of detective work and look deeper at the patterns in this table. So what we're going to do is we're going to expand these output values to show where they come from. As I said, we can see that Diana is starting the year with 10 demon dollars, and we can see that 10 in the table right here in the first row. So if I were to expand, I would say this first row is worth 10. Now the next value is 12, which we calculated by taking that same starting value and adding the 2, which was the pattern that we saw when we went down the table. So we're kind of expanding, where did the 12 come from? It came from taking our starting value and adding 2. Now for the 14, we could say that that is really the 10 that we started with plus the 2 that we added the first time plus the 2 that we added again. We added 2 another time as we moved down to the next row of the table. And we could continue this by saying that 16 is really the 10 that we started with plus the 2 that we added the first time plus the 2 we added the second time, plus another 2, because as we go down the table, we're adding 2 an extra time for each row. Now, as I look at this, I'm noticing there is a pattern to the way that I expanded this representation. Every representation here starts with the number 10, and we add the number 2. The first time, we didn't add the number 2, so we did that 0 times. For the next row, we added the number 2 1 time. Then we added the number 2 twice. Then we added the number 2 3 times. So let's continue to look for patterns here. If I wanted to write this another way, I could say that the first row is 10 plus 2, and I added the 2 0 times for that first row. So I would say times 0. There are 0 2s added to the 10 in that first row. In the second row, I could say that we had the number 10 and we added the number 2 1 time for this row. For the next row, I could say we had the number 10 and we added the number 2, but we did that 2 times. So 2 times 2. And I'm seeing this 1 is that there's 1 2 right here. I'm seeing that there are 2 2s, and in the next row, I'm seeing that there are 3 2s. So I could write this as 10 plus 2, and I added that number 2 3 times. Now, once we've written it in the expanded form, and then we've written it as a pattern, we added the number 2 0 times, we added the number 2 1 time, we added the number 2 2 times, we added the number 2 3 times, there's one more connection that we need to notice. The number of times that we added the 2 matches the week number. For example, in the first row, we added the 2 0 times, which was the input number for that row. For the second row, we added the 2 1 time, which was the input number for that row. For the third one, we added the 2 2 times, which was the input number for that row. And for the next row, we added the 2 3 times, which was the input number for that row. Using this pattern, we can say that depending on what row you're in, whatever week you have, we can calculate how many demon dollars you have by using this same pattern. Now, if we wanted to write this in a general way, here's how we would do that. You should notice that every single expression here starts with the number 10. So this row would still start with the number 10 because that's the same all the time. And every single pattern here, we're adding the number 2. So the equation that we write should have the number 2 in it. Last but not least, how many times did we add that? Well, we just said the number of times we add the pattern matches the input, the number of weeks. Since this is an input of X, we would just put an X here. Now, one last connection we need to make actually goes back to function notation, which we learned in our previous lesson. What we learned is that if your input is X, then your output would be the number of demon dollars. I'm going to call that D. So D of X with X inside the parentheses. This right here at the end, D of X is equal to 10 plus 2 times X, is the explicit equation that we're going to be writing. So the goal for today is going to be able to come up with an equation like this that will allow us to figure out the output values for any input we choose. I could take X and make it a 10. And to figure out the value, I would just plug in the number 10. I could take X and make it a 45, and to figure out how many demon dollars, I would just plug in a 45. So we've created an equation here that will tell us the number of demon dollars for any week of the school year that we want. Now, in this box, it says, write an explicit equation, D of W, to model the number of demon dollars after X number of weeks. This is actually a typo. This should be D of X. And I apologize for that. But if we wanted to do that, the answer to this question, to write an explicit equation, would be this equation we just came up with. So it's always going to look like this. D, which is the output variable, of X, which is the input variable. And don't forget the inputs on the inside, the outputs on the outside. That's what we learned in the previous lesson, is equal to our starting number, which was 10, plus our pattern, which in this case we were adding the number 2. And we did that. We noticed when we wrote it out the long way that the number of times we added matched the number of weeks. So we would just put an X here. This is what's called an explicit equation. Now, why is an explicit equation useful? Well, we can use an explicit equation to find information. For example, if I said evaluate the function for the indicated values, so find d of 2, finding d of 2 really means finding the number of demon dollars after 2 weeks. Because 2 is the input here. It's inside the parentheses. To figure that out, I could just take the number 2, which is right here, and plug it into this equation. So I would have 10 plus 2, and then I would replace the x. I guess I should probably circle that in blue. I would replace the x with a 2. Now that's what we learned in the previous lesson. And if we were to calculate this, 10 plus 2 times 2 would be 14. If we compare this answer to what we know from the table, D of 2 after 2 weeks, we should have had 14 demon dollars, which is what we just figured out using the equation. So this equation checks out. The values from the equation give us the same values that we had in our table. Now, this equation is also useful because it can give us values that are not in the table. For example, if I said find D of 10, this would mean find the number of demon dollars after 10 weeks. Now, our table doesn't go up to 10, so it's a good thing we have this equation, because what we can do now is take the number 10 and plug it into the equation instead of x. So we're going to have 10 plus 2 times 10. I'm just replacing the x with a 10. When I do that, I get 10 plus 20, which is 30. So I'm able to use the equation to get values that were already in the table, which is one of the ways you can check to make sure that your equation is correct. Or you're also able to use the equation to find values that go beyond what was already in your table, so that you don't have to make a super huge table that goes all the way up to 10. You can just use the equation to find those numbers. In general, if we've got an arithmetic sequence, here's how we write the explicit equation. We're going to have f of x, where f is the output variable, which means it could be an f, it could be a d, it could be a whatever you need to use, and x is the input variable. Equals. So an equation has to have an equal sign, so you're going to have f of x equals. Now the way we're going to write this is we're going to use the starting output value. You're going to notice that that's the same thing we used here. The starting output value was 10. Our equation started with 10, so it's always going to be the starting output value. Then you're going to have plus or possibly minus, because arithmetic sequences can have pluses or minuses, and this is depending on the pattern. You're going to have plus or minus the common difference. So whatever amount you're adding or subtracting each time, and then you're going to put a parentheses and you're going to put x, or whatever same variable that you used here. So if you used x here, you're going to use x here. If you use a w here, you're going to use a w here. It's going to be the same variable in both spots. Now, just as a reminder, the common difference, which is something we've practiced a lot in this unit, is always however much you're adding or subtracting each time. Now, this whole idea of expanding the pattern so you can find it is very helpful if you have a table of values, but we don't really need to do that every time. This same thing that we saw here is going to happen every single time. So let's try figuring out an equation without going through the process of expanding the pattern. For example, if I gave you this table of values, could we write an explicit equation? Well, here's what I want you to notice. Our input variable is n. And for the output variable, we're using f. And you'll notice that it's already set up for us to have the n on the inside. So if I want to write an explicit equation, I'm going to start with f of n. And you'll notice that that matches what's here. It matches our pattern of output variable on the outside, input variable on the inside equals. Now, according to what we learned, the first number in your equation should be the starting output. So we're going to start with the number 4, and then we need the pattern. Now, in this table, we are adding 7 each time. So the pattern here would be plus 7. And then we're going to have our input variable again, which is parentheses n. We're going to do that n times. When I look at this equation, the way that I think about it is according to the table, we start with 4 because the table starts with 4. We add the 7, and we're going to do that n times. Let's do one more example where our pattern is actually a subtraction pattern. So in the next problem, we can see that our input variable is x. And we can see that same thing inside of this parentheses, which makes sense because the input variable should be inside the parentheses. Our output variable is g. Our starting value is 36, and the pattern seems to be that we are subtracting 6 each time. So when I write my equation, it's going to look like this. G, which is the output, of x, which is your input, equals start with 36, subtract the 6, and do that x times, where x is the input variable. Now we can also do this in a story problem. So this is kind of go back to kind of the example we did at the beginning, only we're not going to expand the table kind of the long way. We're going to use our shorter pattern that we found. It says the number of students who need to pay fees at the bookstore before the start of school is 150. The number of students who have fees decreases by 15 each week of school. The table below models the function. It says write an explicit equation S of W to model a number of students who have fees after W amount of weeks. So in the directions here, they're telling me use W for weeks and use S for students, where S is the output, W is the input. Now this table starts with 150, which makes sense. We can see that same value in our story problem. And the pattern seems to be subtracting 15 each time, which makes sense because if you look at the table of values, that is the pattern, and it also makes sense because it says decreases by 15. To write this equation, we would write S of W equals start with 150, subtract 15, and do that W times, where W is your input. Here's where it's really helpful to evaluate this equation. It can actually let us check our answer. So we're pretty sure this equation makes sense for this table, but one way to check that is to try plugging in one of these numbers and seeing if you get the matching output. For example, if I said find S of 3, what that means is replace the W with a 3. So in the equation, I would have 150 minus 15 times 3. which gives me 150 minus 45, which is 105. Now that checks out. That is the same input and output combination that I found in my table. When input is 3, the output is 105. So that makes sense. This equation seems to be working. It's giving us a relationship between the inputs and outputs, and that can be really helpful because if I wanted to find S of 8, I could make this table keep going all the way up until 8. But that could take a long time. So instead, my second option is take the number 8 and plug it into the equation that I wrote, which is 150 minus 15 times 8. Now, I am not going to do this in my head. I'm going to go ahead and use my calculator. So I'm going to have 150 minus 15 times 8, which is 30. So my answer here would be 30, which should be the same thing that I got if I made a table that went all the way up to 8. So if I kept subtracting 15, the next one would be 90, and then 75, and then 60, and then 45, and then 30. But you'll notice that this took a little bit longer than just plugging in my number and figuring out the output that way. So I can check that both ways. I would not make a table that went all the way up to my value if this said S of 45. I wouldn't really want to make a table that goes up to 45, so that's why the equation might be faster. Now, in a similar way, we can analyze a pattern that is geometric. So it says here a YouTube channel starts off with 17 subscribers. Each day, the number of subscribers triples. Now, it starts off with 17 subscribers, makes sense in our table because we have a 0 and a 17 here. Our first output is 17. Each day, the number of subscribers triples, which we can see in our table. We can see the pattern of times 3, times 3, and times 3. Again, our goal is to write an equation here, and to do that, we're going to need to unpack the values in this table and write them out in a slightly different way. So I'm going to leave the first row as just 17, but just like previously, we can expand the other numbers to show where they came from. For the second row, I could say that this is 17 times 3. For the next row, I could say that this is 17 times 3 times 3 again. And for the next row, I could say that this is 17 times 3 times 3 times 3 a third time. And I'm getting that by just looking at where those numbers came from. To get 51, I multiplied by 3 once. To get 153, I multiplied by 3 twice. Now, just like before, writing this in a little bit of a different way can help us see the pattern even more clearly. So the first row is 17 times 3, but we multiplied by 3 0 times. So the exponent here would be 0. Now you're going to notice that I'm using an exponent here because when we show that we multiplied over and over, that's where we use an exponent. In the previous example, we were adding over and over. But here where we're multiplying, we need to use an exponent. So I'm going to make a note of that. We need to use an exponent when multiplying or dividing, which means whenever there's a geometric pattern, we're going to be using exponents to show the pattern. For the next row, I would say that this is 17 times 3, and I multiplied by 3 one time. So the exponent would be 1. For the next row, this is 17 times 3, and I multiplied by 3 twice, so the exponent would be 2. And for the next row, this is 17 times 3, and I multiplied by 3 times, so the exponent would be 3. Once again, there's a connection between how many times I used my pattern and the inputs. What we should notice is that the input value matches the exponent 0, 0, 1, 1, 2, 2, 3, 3. So the number of days matches the exponent here. Now that tells me that I can use this same thinking to write an equation where if the input is x, I can write an equation to find the output. Just like before, we're going to have for subscribers, I'm going to use the letter S, and for days, I'm going to use the letter X because that's what I'm using here. So I would say S of X for this output, because it's the output for X days, will be equal to, now every single representation here starts with the number 17. So 17, and every single expression here, we're going to multiply by 3, and we're going to multiply by 3 the number of times that matches the input. So if the input is X, the exponent should be X. Now this right here, again, is what we call an explicit equation. So this explicit equation would be S of X is equal to our starting value, which is 17, times 3, because that was the pattern, and I'm going to do that X times, so the exponent is X. Now we can check this equation to make sure that it actually does match the table of values and the story that we were given. And we can do that by evaluating this equation for one of the numbers we know. For example, we know that after one day, there should be 51 subscribers. So to figure this out and to make sure the equation is correct, I could take the number 1 and just plug it into the equation instead of the X, which means I have 17 times 3 to the first power. Now I could use my calculator here, or I could know that 17 times 3 is 51, which checks out. It matches the input-output combination in the table. For S of 7, I would just replace the X with a 7. So I would have 17 times 3 to the 7th. And again, I'm going to use a calculator here because I don't know what 3 to the 7th is off the top of my head. So I'm going to have 17 times 3 to the 7th, which is 37,179. I could, if I wanted to, make this table go all the way up to the number 7, but a faster way to get this value for a value that's beyond the edge of the table is just to plug in that number to the equation. In general, when you want to write a geometric sequence equation, an explicit equation, you're going to do the output variable, parentheses, the input variable. So this is always the output, whatever you're choosing to use for your output variable, and then parentheses, your input variable, is equal to your starting output value. So just like our arithmetic, we're using our starting output value at the beginning. Then you're going to have times your pattern, which we call the common ratio. And then you would have, instead of parentheses x, you would have an exponent. Because when you're doing repeated multiplication, you always have to use an exponent. Now, there is one common mistake that we see fairly regularly with geometric. When a geometric sequence has a dividing pattern, we must use a fraction to represent that pattern in the equation. So for example, if the pattern is dividing by 3, then in the equation, we would write times 1/3. If the pattern is dividing by 7, then in the equation, we would write times 1/7. And we've seen that before. It's just a reminder that you can't use division in an equation. It is illegal. You can't call that a common ratio. So let's go ahead and try writing an explicit equation for the following tables. So the first thing to notice is that this first table, our input variable is n, our output variable is f, our starting value is 4, and our pattern seems to be multiplying by 3 each time. So to write the equation, we would say f, which is our output variable, of n, which is our input variable, equals our starting with 4, multiply by 3, and multiply n times, which is why the exponent is n. You'll notice this is a very similar thinking pattern to what we did with arithmetic. It's just we're using multiplication now. For the next table, we've got a starting value of 600. Our pattern is we are dividing by 2. And it looks like our input variable is x, our output is g. So we would have g, our output variable, of x, our input variable, is equal to, start with 600. Now, this is where that common mistake comes in. If we're dividing by 2, we need to write times 1/2. So times 1/2, which is our common ratio, to the x power. Now, when you've got a fraction here as your common ratio, it's important to put that in parentheses with the x on the outside to show that you're raising that entire fraction to the x power. Again, we can apply this in a modeling situation. So at the start of sales, there were 400 students who still needed to pre-order their books. Each hour, the number of students who still needed to pre-order was cut in half. Now we can see a couple important pieces of information here. There were 400 students at the start, and we can see that 400 in the table here. Each hour, the number of students was cut in half, and we can see that pattern because this is times 1/2, times 1/2, times 1/2. Another way to think about that is dividing by 2, which we would still write as times 1/2 in an equation. Now it's telling me here, write an explicit equation P of H to model the number of students who have fees after H hours. Now H is the input, so we're using H for hours, and I can tell that because it's inside the parentheses, and P is the output, and I can tell that because it's outside the parentheses. So my equation would be P of H equals, and then I would start with 400, multiply by 1/2, and my exponent, because again this is multiplication, would be h, which means I'm going to put this in parentheses. I can check this equation by substituting some values. So it says here P of 3, which is a value that I know, and I want the answer to be 50. I can check my equation by taking the number 3 and plugging it in instead of the h, which means I'm going to have 400 times 1/2 to the h power. Now, again, I'm going to do this on my, to the third power. My bad. Again, I'm going to do this on my calculator because I want to make sure that I'm not, getting this wrong because my arithmetic is not going well. So 400 parentheses. Now to make a fraction, I'm going to hit alpha and then y equals, and you can see that it says n over d here. And I'm going to have 1 over 2 parentheses to the third power, which gives me 50. Which checks out. It matches the input-output row of the table where I have the input of 3 and the output of 50. I can also use this equation to predict what's going to happen if I were to make my table bigger. So what would P of 5 be? Again, my input is going to be 5. So in my equation, I'm going to have 400 times 1/2 to the 5th power. We're going to go through kind of how to type this in one more time. I know there's a lot of buttons to learn where they are. So we're going to have 400 parentheses. Now I'm going to hit alpha, which is right here, and then y equals, and the first one says n over d, numerator over denominator, 1 over 2, and I'm just using these arrows to move to the next thing. Then I'm going to get out of the denominator, parentheses, to the fifth, which is 12 and a half, or in other words, 12.5. And you can write your answer as a fraction or a decimal. I don't really mind either way. All right, that is it for our video today. Thank you guys so much for watching, and I hope I get to see you soon.